Okay, so in the movie business, sequels are all the rage. So this is actually the sequel to lesson 6.5 and 6.6 day 1. So in that lesson we talked about finding all roots of polynomial equations. And in the sequel we're going to continue on with that theme. And there actually is a warm-up to do for the sequel for this lesson. So if you take a moment, pause the video, and answer the questions listed here. And it asks you to fill in each of the statements to make them true using this given information. If 5 is a root of some polynomial, p of x is equal to 0, then I want you to fill in the blank for each of these. So please pause the video now and complete the warm-up. Okay, so if 5 is a root of p of x is equal to 0, then what that means is, number 1, that p of 5 is equal to 0. In other words, if we were to substitute in 5 into this, whatever this polynomial function is, we would get an output of 0. Number 2, that means that 5 is an x-intercept of the graph of p of x. It's the place on the x-axis where this polynomial's graph will cross. Number 3, that means that x minus 5 must be a factor, binomial factor of p of x, because that root of 5, if I substituted it into x minus 5, would make it into 0. So that's how I know that x minus 5 is one of the binomial factors. Number 4, when you divide this polynomial p of x by x minus 5, this binomial, you'll get a remainder of 0. That's what it means to be a factor of, or to be divisible by. And finally, number 5, that means that 5 is a root, or a 0, of the graph of p of x. Okay, so you know, you go to the movie theater and you see the trailers for all these sequels that are coming out. Well, these learning goals here are kind of like our trailer. They're kind of the coming attractions. So the coming attractions in this lesson are to, first of all, we're going to define and identify multiplicity of roots of polynomial functions in factored form or from a graph. Secondly, we're going to learn to write polynomial functions given all rational zeros. And finally, we're going to use understanding of conjugate, irrational, and imaginary root pairs to write polynomials given some of their zeros, which probably to the outsider reading these learning goals, they seem a little intimidating, but it is really kind of right in line with things that we've been studying. And so words like conjugate and irrational and imaginary roots hopefully don't intimidate you too much. So that's kind of what you have in store for you in the sequel to lesson 6.5 and 6.6. So sometimes a polynomial equation has a factor that appears more than once. This creates a multiple root. I included here an example of a type of it's a quadratic equation that has a multiple root. This happens to be a perfect square trinomial, and when it's factored, it gives you two binomials that are identical, which would then produce the same solution 2 times. That's what we mean by multiplicity, when a particular solution counts for more than just one of the solutions. And in this case, because we have a quadratic equation, we anticipate that we would get 2 solutions for the most part, and these actually are 2 solutions. It's just that it's the same number. So each one of those, or that -3 actually counts for 2 separate solutions. So if we were to take a look at a little more complicated quadratic polynomial function, like 3x to the 5th plus 18x to the 4th plus 27x cubed is equal to 0, and I were to take out the greatest common factor of 3x cubed, that would actually leave me with sort of that exact same quadratic equation that I just factored, x squared plus 6x plus 9, and so that would produce these 2 binomial factors of x plus 3 and x plus 3. And then if we were to actually set those factors equal to 0 and using that zero product property, I would see that I got these 2 solutions, 0 and -3. Well, it turns out the 0 actually accounts for 3 of the solutions, and that's because it comes from a factor 3x cubed that actually has a degree of 3. And the x is equal to negative 3 actually counts for two solutions because it comes from a factor x plus 3 that actually was degree 2 because it was x plus 3 squared. And so we could say that those two roots or zeros of 0 and negative 3, well, the 0 has multiplicity 3 and the negative 3 has multiplicity 2. And if we wanted to generalize this finding, this idea, we would refer to what's called the fundamental theorem of algebra, which says this: every polynomial function of degree n of 1 or more has exactly n zeros, including multiplicity. So we were expecting to get 5 zeros or roots from that polynomial equation, and we actually did. It's just that there was two different roots that each counted for more than just one. One of them that counted for 3 and the other counted for 2, and so in a sum of 5 solutions. So to kind of summarize that, the degree of that polynomial was a 5, and the degree of the factor 3x to the third was 3, and so that root x equals 0 had multiplicity of 3. And the degree of the factor x plus 3, which was actually x plus 3 squared, had a degree of 2. And the multiplicity of that root of negative 3 then was... So let's go ahead and turn the page and look at some examples. Okay, so now that we know a little bit about this whole idea of multiplicity, let's identify the roots for each of these given equations and then state the multiplicity of the root. So this first polynomial equation, notice that we have some pretty high degrees here. In fact, this is a degree 6, and so based on that fundamental theorem of algebra, there should be 6 roots for this equation. And so to find the roots, I'm going to start off trying to factor this. So right away I noticed that all of the terms have a greatest common factor. And the greatest common factor is 2x to the 4th. So I'm going to go ahead and factor out 2x to the 4th power, and that's going to leave me with x squared minus 5x minus 6. And I know that that is a quadratic equation that can actually be broken down further. And so I'm going to go ahead and factor that. I'm looking for, I know that both of these binomials are going to start off with x, because x times x is x squared. And so now I'm looking for factors that multiply to give me negative 6 that are going to also add to negative 5. So right away I know that because they have to multiply to give a negative, they're going to have opposite signs. And so I thought of right away negative 6 and 1. And those do fit the bill because they multiply to give this negative 6 and they add to give me that positive or negative 5 that I need, excuse me. So if I looked at each one of these factors, I know that if I use the zero product property and set them equal to 0, the x minus 6, that binomial, would indicate a 0 or a root of a positive 6. The x plus 1 would indicate a root of a negative 1. So that's 2 of the 6 possible solutions. Well, where do the other 4 come from? Well, if I set 2x to the 4th power equal to 0, the only value of x that could make 2x to the 4th 0 is, in fact, 0 itself. And so that means 0 is one of the solutions. And so I'm out of factors to set equal to 0. So where am I getting these 6 roots? Well, that's because this 0 actually counts for 4 solutions. It has multiplicity 4. And I know that because that 2x to the 4th power is a degree 4 factor. And so this actually accounts for 4 of those solutions. Each of the others account for just 1. And so therefore, my 3 solutions are 0, 6, and negative 1, with 0 having multiplicity of 4. Okay, let's try another one. So example B, is hopefully one of those ones that you recognize that was similar to things that we had done in the last two lessons. It's this sort of like a fake quadratic. X to the fourth minus 13x squared plus 36 sort of kind of mimics the pattern that we would have see that if this instead had been x squared minus 13x plus 36, if we kind of thought about factoring that, we would start off both our binomials with an x, but because this one starts off with an x to the fourth, we're going to start them both off with x squared. And then because I know that the two other terms in the binomials have to multiply to give me a positive 36, but they also have to add to give me a negative 13. And so I thought about right away they have to be the same sign factors to multiply to give me a positive. But since they have to add to a negative, they're both going to have to be negative. So both of these are going to be a minus, and the two numbers that kind of fit the bill here are 4 and 9, because 4 times 9, well, negative 4 times negative 9 is positive 36, and those same two numbers add to give me that negative 13 in the center. But in fact, these binomial factors can be broken down further. They're both difference of square special pattern, which means they have binomial factors that are nearly identical, but one is a plus and one is a minus. We'll take a look at the first one, x squared minus 4. That's going to give us an x plus 2 and an x minus 2. And then the x squared minus 9 is going to give us an x plus 3 and an x minus 3. And so from that, I can see that the solutions are going to be negative 2, 2, negative 3, and 3. And that actually accounts for all four that I need. And that means that each one of those must have multiplicity of 1. So I have the 4 solutions, each counting for 1. Now, unfortunately, most of the time, like in your homework or in your practice sets, the polynomials with only integer roots are not going to be always factorable. And so we must use their graphs instead to determine the multiplicity of roots. So this little table gives a summary of how we can tell from a graph what the multiplicity of each of the roots must be. And of course, you want to keep in mind that the total number of zeros or roots will always equal the degree of the polynomial. So we have multiplicity that we've seen so far. We've seen some had multiplicity 1, some 4, we saw some 2s and 3s on the other side. And so we could actually break down multiplicity into two categories. One being even multiplicity, and then the other being odd multiplicity. So if we have even multiplicity, such as when we had multiplicity 2 or 4, roots with even multiplicity, their graphs will actually touch the x-axis. So those roots, the graph will come up and touch the x-axis, but will not cross through it. And so you'll see it come up if it's even and touch the x-axis and then turn around and come back down. And that would indicate an even multiplicity. An odd multiplicity, there's two different possibilities. If there's the multiplicity of just 1, so in other words, if it counts as just a single solution, you'll see the graph just cut right through the x-axis, just cross on right through. But if the multiplicity is an odd number greater than 1, then it's going to cross by bending through the x-axis. And I think we'll go ahead and take a look at this graph below, and I think that'll make more sense to you what we're talking about as far as going straight through or bending through or just touching the x-axis. So here is a graph of 3x to the 5th plus 18x to the 4th plus 27x cubed equals 0, which actually was one of the polynomial functions we looked at actually on the first page of the notes. And so this is actually what the graph looks like. And you'll see from the graph that this graph crosses the x-axis, actually intersects the x-axis 2 times. One here at negative 3, 0, and the other one at 0, 0. So what we were talking about with this even multiplicity, we said even multiple roots would come up and touch the x-axis but not actually cross over it. And you can see this really kind of going on right at this -3 right here. So what's going on here is see how it's coming up and touching the x-axis and then turning and going back down. And then this idea of crossing or bending through the x-axis, that actually is going on right here. You'll see it's kind of going up, it's hitting the x-axis, then it's kind of curving and bending and then crossing through. It's not just cutting right through, it's kind of meandering, kind of taking its time to pass through. It crosses or curves up, touches it, and then continues and curves on the other side. So if we look at that, that polynomial function, the total number of roots of this polynomial will have to be 5, and that's because it's a degree 5. And from the graph, we can actually identify 2 roots. Just as I said before, we can see them listed right on there at -3, 0, and 0. The roots are -3 and 0. And as I mentioned, this -3 actually has an even multiplicity. And this, because it kind of conforms to that behavior where it's coming up and touching the x-axis and then turning and going back down, or it's not actually crossing over the x-axis. And this one has odd multiplicity, and so that means that the multiplicity of the root x equals -3 must be 2, and the multiplicity of the root 0 must be 3, because then the multiplicities add up to that 5. And that's why I know that that -3 can't be a different even number. It can't be 4 or 6 or 8, because the maximum roots I can have is 5, and because that 0 certainly does not have multiplicity of 1, it's not just cutting right through the x-axis, then it must have an odd number. And so the only odd and even number combinations that would add up to 5 would be 2 and 3. Let's go ahead and take a look at another example on the next page. So this time I see a graph of x cubed plus 6x squared plus 12x plus 8 equals 0. And I know that by looking at this polynomial function that the total number of roots for this polynomial must be 3, and that's because this is a degree 3. And if I look at the graph, I only see one place where this actually encounters the x-axis, and I can see here that it must be when x equals -2. So that solution right there is at -2, 0, and that means that the 0 is -2. And so I know it's x equals -2. But I don't see any other ones, but that's okay, because I can tell by the behavior of that graph, as that graph is kind of coming up and like bending through the x-axis, that must have odd multiplicity, and it's not an odd number of 1 because it's not cutting straight through, and so it's bending through, and that means that -2 actually will account for 3 solutions, and the multiplicity of that then is 3. Now sometimes that odd multiplicity is a little bit tricky. I think this next example will really help you kind of clarify that. You see this graph, and it is of x to the 4th plus 8x cubed plus 18x squared minus 27. So I am looking for 4 roots, and I know that because of the degree is 4. And if you look at the graph, and I continue, it looks like it comes down and dips down here below where I can see it, but then it comes back up like this. And so I can actually see that it's crossing right here, and then again right here. And I don't know exactly what that solution is. I'm going to guess it's 1. And in fact, it has to be 1 because I just substituted 1 into the function and I got 0, so I know that's what it is. So this one's right here at 1, and this one is right here at -3. And so the difference between these in terms of the multiplicity that they each represent, this x equals -3 actually is going to represent odd multiplicity that's greater than 1, because see how it's actually bending through, it's kind of curving through the x-axis, whereas the one that's at 1, that one actually is cutting straight through the x-axis. So that means the x equals -3 has multiplicity of 3, and the x equals 1 has multiplicity of 1. And so those together give me the 4 roots that I need. Okay, so I went ahead and graphed this next one, -2x to the 5th. plus 26x cubed minus 72x equals 0. And I changed the window because to make it a little easier to see the solutions. And I could see that this graph crossed 1, 2, 3, 4, 5 times. And what that means is this, that each one of these must only have multiplicity 1, and that they do definitely fit that characteristic of multiplicity being 1, because each one of these spots on the graph is cutting straight through the x-axis. There's no curving through, it's just cutting right straight through. And so I know that each one of these counts as 1. So whatever those solutions are, if I were able to see them and say find them in the table, whatever they might be, each one has multiplicity 1. Now we're going to go ahead and just cross out example C. There's something a little bit funny about that. I checked that out on the calculator already, so we're just going to, I think we've seen enough to kind of get an idea of what multiplicity looks like on the graph. And certainly in the practice sets we'll see some more. So let's go ahead and continue on with the next learning goal and turn the page. Okay, so the next learning goal was to write polynomial functions if we're given the roots. So let's see, example A says the roots of this polynomial equation are -1, 1/2, and 4. Now, we're not told anything about multiplicity or anything, so what we can assume is that since there are 3 roots, this is going to be a third degree or a cubic equation. And if we think about back to quadratics, when we studied quadratics, we did the same thing with quadratic equations. When we were given the 2 roots or zeros, we were able to work backwards to come up with the binomial terms that must have produced those roots, and then expand those out to actually find the polynomial function. So taking a look at this first root of -1, if we had a root of -1, that means it must have come from a binomial factor of x plus 1, because plugging in a -1 in for x would produce a value of 0. And when we talk about roots, we really mean zeros. If we looked at the half, it would be it would come from a binomial factor of x minus a half, and then the 4 would give us a binomial of x minus 4. And so if we wanted to write a polynomial function with these 3 roots, the simplest one, in fact, then we would just have to expand this out using FOIL. So remember from an earlier lesson in this chapter, if you have 3 binomials that you want to multiply, you start off with a pair of them. So for instance, say I wanted to multiply these 2 binomials, I'd go ahead and FOIL those out, and then whatever I get, I would distribute that x plus 1 through. And really I could have picked any 2 to start with. So when I use FOIL here, multiply the first 2, x times x is x squared. The outside 2 would give me a minus 4x. The inside 2 would give me a minus 1/2 x. And the last 2 would give me a positive 2. And put my like terms together would give me x squared minus 4.5 x plus 2. And now I want to take that and I'm going to distribute this. I'm going to bring that x plus 1 down and I'm going to distribute that through, and that'll give me my final polynomial. And so the x distributed through, x times x squared is x cubed, x times minus 4.5x is minus 4.5 x squared, x times 2 is 2x, and then distribute the 1 through, 1 times x squared is x squared, 1 times minus 4.5x is minus 4.5x, and 1 times 2 is 2, and then like terms. So let's see, we have no other x cubed terms. So I can start off with my x cubed. Then I've got some x squared terms. I have the minus 4.5x and the plus 1 x squared. Put those together, that gives me minus 3.5 x squared. So those are done. And then I'm looking for my x terms. And so I have some x terms. I have a 2x and a minus 4.5x. Combine those together, it gives me minus 2.5 x. And then finally the plus 2. And so the polynomial function that would have these 2 zeros would be x cubed minus 3.5x squared minus 2.5x plus 2. Here's what the graph would look like of that function I just wrote. I entered this into the grapher, and it's clear that this graph does verify that those are the solutions to this polynomial function that I just wrote. You can see in the graph where it crosses about here, which looks like it's -1/2, that was one of the roots. Another time at 1/2, and then over here also at 4. And if you look at the table, you can see that solution there at -1. You can see the one down here at 4, and you can't see the other one in this table, and that's because the x's are scaled by 1s, they're just integer values. But you can see that between 0 and 1 here, which is where the half would be, that the sign has changed on the output, which means it's crossed over from above the x-axis to below. So there's obviously been some intersection in the meantime, and that was what was going on right here on the graph. So the graph is consistent with what the roots were, and that polynomial function then is a representation as one of the possible polynomials that would have those 3 roots. So conjugate root pairs. If a polynomial p of x has rational coefficients and the square root of a is one of the roots of p of x, then so is its conjugate the opposite of the square root of a. Now, anytime we take a square root, we always know that there's a positive and a negative version. So anytime that occurs as we're solving some sort of polynomial equation, that produces 2 different solutions, one with a positive square root of this number a and one with the negative square root of this number a. Now, you may remember that this also occurred when we had some of these complex solutions. So likewise, if a polynomial p of x has rational coefficients and bi is a root of p of x, then so is its conjugate negative bi. The reason why that is remember that these imaginary roots come from taking the square root of a negative number. And so it comes right back to this whole idea of the fact that when we take a square root, there's a positive and a negative version. And so that creates another conjugate root. And so when we're trying to write polynomial functions, when some of the roots are square root solutions, or when there's complex zeros, we have to keep that in mind and remember that those always come in pairs, conjugate root pairs. Here's an example you see this come into play. So it says, write the simplest function with the given zeros of 5 and 2i. Well, we know that there can't be just those two solutions, 5 and 2i. If 2i is one of the solutions, then so must also be negative 2i. So in actuality, there actually are 3 zeros for this polynomial function, which means it's, unless there's some sort of multiplicity here, then it's a cubic function. So our first step was to identify all the roots, and I just did that. And then write each of one of these zeros, write the binomial that each of those come from. In other words, write the equation in factored form. So this 5 would produce a binomial factor of x minus 5. That way if I plugged 5 in for x, that would give me 0. And the 2i would be x minus 2i. And the negative 2i would be x plus 2i. Now, just as in the prior example, when we want to find this polynomial function, we have to expand this out. And really, at that point, you can multiply any 2 of the binomials together to start, but the smartest ones to start with would be the 2 that have the complex roots in them. And so that's what we're going to do. We're going to start with multiplying the x minus 2i and the x plus 2i together. And you may remember that if we have conjugates, which these are conjugates, multiplying 2 conjugates together will produce a real number. And this is how this happens. When I multiply the first 2, x times x, that's x squared. The 2 outside terms I would get a positive 2i times x. The two inside terms would give me a minus 2i times x, and the last two would be a negative 2i times a positive 2i would be a negative 4i squared. Well, you can see clearly that those two middle terms are opposites. They cancel each other out. And remember that I squared really is negative 1. So this is really saying negative 4 times negative 1, which makes that positive 4. And so this whole thing reduces down to x squared plus 4. So now I could continue on expanding by then multiplying the x minus 4 through. And I can use FOIL or just distribute. If I multiplied using FOIL, the first two, x times x squared is x cubed. Outside 2, 4 times x is 4x. Inside 2, minus 5 times x squared is minus 5x squared. And then the last would be minus 20. So then if I put it in that standard form, this polynomial p of x must be equal to x cubed minus 5x squared plus 4x minus 20. Now, if you were trying to verify this polynomial function by graphing it, just keep this in mind. Remember that you're only going to actually see one of these zeros. You only see one place where this graph is going to cross the x-axis, and it's going to cross at 5, because the other two are these imaginary solutions. So they're not actually crossing the real x-axis. Let's go ahead and turn the page and look at one last example. So this last example has two different parts, A or B and C. And notice that in both cases, they're just listing two roots. But remember, if you have a root that has a radical in it, then it has a conjugate pair. And also, if you have imaginary solutions, if you have imaginary zeros, complex zeros, then you're also going to have a conjugate pair to go with it, even if it's not listed. So in actuality, in example B, we really actually have three roots that are implied for this function. There's 2, there's the square root of 3, and negative square root of 3. Down here in example C, I have a 5i and a square root of 3, which also means that I have a negative 5i and a negative square root of 3, because those always come in pairs. Example B's binomial factors then would be x minus 2, x minus the square root of 3, and x plus the square root of 3. So to expand out these binomials, I again want to pick the ones that are these conjugate root pairs to multiply together first. So I'm going to start off with these two binomials and use FOIL. X times x, that's x squared. Outside 2, positive square root of 3x. Inside 2, minus square root of 3x. Last 2, minus square root of 3 times positive square root of 3. That gives me a negative, and square root of 3 times square root of 3 is 3. And so then putting my like terms together and canceling out those middle terms leaves me with just x squared minus 3, which then I have to multiply by x minus 2. So if I distribute that x minus 2 through, I have x times x squared, that's x cubed, x times minus 3, which is minus 3x, minus 2 times x squared is minus 2x squared, and minus 2 times minus 3 is plus 6, and then put that in standard form to get my polynomial x cubed minus 2x squared minus 3x plus 6. And since C seems to be the most complicated of all, we'll go ahead and do this one together as well. So the two binomial factors that come from 5i and negative 5i would be our x minus 5i and our x plus 5i. And then with the two radical solutions, those would be x minus square root of 3 and x plus the square root of 3. Now this time we have 4 binomials to multiply, and really the best way to do that again is to match up these conjugate root pairs. So if I put these two together, multiply those, put these two together, multiply those, and then whatever I get, multiply those final things together. So we can just start working on this x minus the square root of 3, x plus the square root of 3, the x times x is x squared, outside 2, square root of 3x, inside 2 minus square root of 3x. Last 2 is minus 3. Put the like terms together, and this whole thing becomes x squared minus 3, as we saw in the example above. Go ahead and go over here and work on the imaginary ones, the x minus 5i and x plus 5i. X times x is x squared, outside 2, 5ix, inside 2 minus 5ix, and the last 2 will be a minus 25i squared. I'm just going to draw a little line down here to divide these up and put my like terms together. So of course the middle terms will cancel out. I can replace that was supposed to be an I squared. Replace that I squared with a negative 1. That turns this into negative 25 times negative 1, which is a positive 25. And so this is x squared plus 25. And then finally, I can multiply these two together to get my expanded, simplified in standard form polynomial. So the first two, x to the fourth times x to the fourth is, x squared times x squared is x to the fourth. It's the first two, outside 2 minus 3x squared, inside 2 plus 25x squared. And then the last two would be minus 75. And then I can group my like terms together here, and I get x to the fourth plus 22x squared minus 75. And that's going to wrap it up for today's lesson. So I'll see you in class.